Hello everyone, I'm Orshan, a data scientist at Outbrain. During this upcoming session, I will be introducing a paper that I co-authored with Natalia and Asaf from Outbrain as well. Our paper is titled Combating Ad Fatigue via Frequency-Recency Features in Online Advertising Systems. While this is considerably a long title, it basically could be summarized into this meme in front of you. The all too familiar situation where you keep seeing the same ad over and over again. Some users might get bored when they see the same ad repeatedly. Some would get annoyed, and some would just be disappointed that this ad keeps coming, like this guy in the picture. This phenomenon is called ad fatigue. It's one of the main problems in recommendation systems, and we suggest here a solution for it. So to understand how we addressed this challenge, it's important to get a picture of what Outbrain is. The quality of recommendation in online advertising system can make a real business impact. This is also the case for us in Outbrain. Outbrain is an online advertising platform that serves as a bridge between advertisers and publishers, like Sky News, CNN, and Washington Post. We employ machine learning models to match ads with the users across various websites and mobile apps. Our revenue stream is directly linked to user engagement, particularly when users click on the sponsored content we recommended to them. It's a large-scale system which serves 11 billion ads per day to millions of users. Let's simplify the system flow to better understand it. Meet Emma, a daily CNN feed scroller. Each morning, when she scrolls down the CNN feed, a request is sent to Outbrain, and our task is to determine which ads are most likely to catch Emma's attention and gets her to click in the predefined yellow slots here. We have a set of candidate ads for this purpose. In this case, it's 3 ads, but usually it's thousands. We extract various features from each ad, such as image characteristic, titles, and additional information. We also consider user features, like viewed ad history, and contextual features, like the time of day, to make the best decision about which ad to place in the available slots. All of these features are fed into a click prediction model. A click prediction model estimates the likelihood that a user will click on a specific ad. Specifically, we employ a deep field-aware factorization machine model, which is a non-recommendation model. While we won't delve into the details of this model's architecture here, you can think of it as any other machine learning model that takes an input and provides a prediction. In our case, prediction for a click, ranging from 0 to 1. Next, we rank the ads based on the prediction we got and by the advertiser's cost per click, which is the amount they are willing to pay for each click. So in our scenario, the model determined that Emma will be recommended to buy some pudding molds, as it's the top ranked ad appeared in the first available slot. Or perhaps consider starting a fitness program with this second ad chosen here. The illustration I just provided focused on a single request, but Emma, like many other users, generate multiple requests within each passing minute or even second. This implies about the issue we are aiming to solve. Given the same user, similar context, and similar set of ads, the model tends to recommend the same ads to the same user, leading to ad fatigue. Ad fatigue negatively impacts all the players in the marketplace. It harms the user experience, causes a decrease in traffic for publishers, resulting in revenue loss. It also leads advertisers to spend their budget inefficiently on unsuitable users, potentially damage their reputation. The negative impact of ad fatigue can be also shown in the next graph. It showcases the average CTR per frequency value, using 1 billion samples from our data. CTR, click-through rate, is calculated by dividing the number of clicks by the total number of recommendations or ads displayed. The term frequency refers to the number of times the ad has been presented to the same user in the past. So to illustrate, let's consider Emma, a typical user. Her chance of clicking on the pudding mold ad reduces by 37% if she had previously encountered this ad 3 times compared to her initial encounter with the ad. This decline continues, reaching a 72% decrease when Emma has viewed the same ad 10 times before. It's important to note that the CTR here is normalized by the CTR of frequency value 0, and it's also averaged, which means there could be variations in each individual user-ad interaction. The following graph takes into consideration the element of recency. The purple line is the same line as in the previous slide. Illustrate the frequency over a week, whereas the red line demonstrates the frequency within the last hour. This allows us to distinguish between scenarios. For instance, where Emma viewed the same pudding mod ad 5 times in the previous week versus 5 times in the last hour. The latter scenario is undoubtedly more irritating for most users, as you would likely agree. So ad fatigue definitely demands a solution. A common but naive approach to tackle it is through what we refer to as a hard frequency capping, which simply restricts the number of times each ad is shown to every user. However, achieving an optimal balance is quite challenging and often results in reduced revenue, primarily because users have different preferences from one to another. Moreover, this method doesn't take into account the potential opportunity cost of presenting a new ad as an alternative to a repeated one. Sometimes a repeated ad will be more profitable for various reasons. A more effective approach could involve integrating this data into a machine learning model. This directly leads us to our approach we have named FORI, Frequency over Recency Intervals. Rather than implementing rigid limitations, we created features for our click prediction model. Here is how it works. When we receive a request from Emma, our repetitive example, we take into account the week before the request and segment it into time intervals. Within each interval, we count the previous interactions with the pudding model. These intervals increase exponentially as we move further from Emma request time, placing more emphasis on recent interactions. Each of these intervals is then inputted into the model as a feature. This methodology has proven effective for us, as we will demonstrate in the forthcoming results. Because first, FORI features are optimized alongside all other model features, ensuring they align accurately within each individual user interest. Second, it factors in recency, which we have proved as critical. Lastly, the use of non-overlapping intervals aids in reducing noise and enhancing the model's learning capability. Our offline results showed a promising 0.38% increase in log-logs metrics compared to a model without FORI features. While this might appear to be a modest improvement, it is considered substantial in our case since Outbrain is a large-scale platform. It also bears statistical significance. More importantly, we performed a large-scale online A/B test across a 14-day period over our production traffic. We evaluated the model incorporating FORI features against one that didn't. This test led us to a 0.84 increase in CTR and a 0.74% boost in revenue. This signifies a dramatic annual revenue growth for us. Last but not least, we supplied evidence of reduction in ad fatigue. While the graph might seem a bit complicated, I will try to simplify it. We refer to the same A/B test as mentioned in the previous slide, but in this case, we are comparing the number of served recommendations across each frequency group. Let's delve into it. We measured the number of recommendations served at each frequency by both models, Model A and Model B. We then calculate the lift or drop by dividing one by the other. For instance, the new model with FORI features shows 10% less recommendations, which we were already viewed by the user 11 times before. It means it prefers to display other ad candidates instead, candidates with less repetitive history. We notice this trend from frequency 3 and beyond. Furthermore, by examining the display ads lift in frequency number 0, we noticed that users are exposed to a greater variety of ads they never saw before with the new model. This implies that the new model, equipped with FORI features, tend to display more new ads than the model without FORI features. This was a significant finding for us, as one of our objectives is to diversify the ads display. It also confirmed that the model is behaving as expected, which is not such an obvious thing with deep models today. In conclusion, we have effectively reduced ad fatigue within our system. We enhanced user experience and achieved a substantial increase in revenue. The Fourier approach can be seamlessly adopted in any other user item domain. Is that relevant to you? Thank you very much for your attention.